Okay, welcome back, everybody. I hope the midterm break was nice, and that you didn't have to do too much shoveling or anything like that. I guess probably most people saw that we actually broke the record for the snowiest month in history. Recorded history. There was ice ages and stuff. There might have been more snow down, but in terms of recorded history, since they started writing it down, we had the snowiest month ever in February. With more than 170 centimeters of snow. Very interesting. Okay, so I'll just give sort of a reminder of sort of where we are headed. And I'll also just mention, so for anybody who came in late, the midterms, there's a couple people who haven't picked up the midterm yet. They're just in a little stack here. You can get them at the end of class. The midterm was very well done in general, so the average was 79, almost an A. And there were a couple of lower marks. If you did get one of the lower marks, don't worry about it too much because the midterm is only worth 20%. And so there'll be lots of chances to make it up on the second midterm or on the final. And the assignments also count for a fair bit, 25%. There was a question before a few people walked in about the second midterm. So the second midterm is in about I think it's 6 class sessions from now. I think there's 5 class meetings and then there's the midterm. And the midterm is the second midterm will basically focus strongly on what's covered in those classes. So there may be sort of prerequisite material from the first midterm, but there won't be any explicit questions on the stuff that was already covered on the first midterm. But you still will need to know stuff like, what's a velocity field, what's a gradient, that kind of thing. But they'll just be implicitly involved in the questions. What else? I don't think there's anything else major. Does anyone have any questions about the structure or timeline? Okay. So what we've been doing for the past few classes is we're trying to develop a set of equations that will allow us to predict what the velocity field will be in the future. So this is sort of, it's an analogy for what we do in numeric weather prediction, weather forecasting. We observe the state of the atmosphere, or if it's an ocean forecast, the state of the ocean at some time, and then we want to predict what's it going to look like in the future, like what are the winds or the ocean currents going to look like. So in the first part of the course, we were talking a lot about if you were given a velocity field, how do you compute accelerations, how do you compute particle trajectories, solve the kinematic equation, that sort of stuff. And that was the focus of the first midterm. But now we're really trying to ask, where does that velocity field come from? So if we don't know what the flow is, how do we figure out what it ought to be based on physical concepts like forces and energy and stuff like that? And so a couple classes ago, we derived our first equation that looks like it can predict a velocity field. So in general, an equation can predict something into the future if it has a derivative with respect to time of that thing. So if you have an equation that has, for example, like d temperature d time equals some stuff, then you can predict temperature using this equation. Because if you solve it, you'll get a solution t of t, the temperature as a function of time. So this equation here, Euler's momentum equation, we derived this based on essentially using Newton's second law, F equals ma, applied to Lagrangian parcels of fluid. And this looks like a good candidate to predict a fluid velocity field because it has that time derivative of velocity. It's actually wrapped up in the material derivative, but there is a partial time derivative in here, and so that allows us to predict what the velocity will be at a future time, if we know what it is at some initial time. But we found that there's a problem with using just this equation. We're not quite done yet. Because this equation has 5 different variables in it. So u vector is u/v/w. So there's three variables there, u/v/w, and then pressure and density are also both in the equation. And so so we have five variables, but we only have 3 equations because it's a 3-coordinate vector equation. So there's du dt, dv dt, and dw dt. So we have 5 unknowns and 3 equations. So we need to get some more information somehow to incorporate into our system to allow us to solve it. And so last time we started talking about how we can do that. And one general idea is to use other conservation principles or other physical principles from physics to get more equations that we can then combine with the Euler momentum equation to be able to start solving them. And we talked about what's another thing that's conserved in physics. Well, conservation of mass is generally something that's we believe is true. And we started analyzing how mass enters into and leaves a certain region. So we basically imagined that in our flow somewhere, we have an imaginary box, so just an imaginary cube. And so it's not a material cube, so it's not a Lagrangian parcel, so it doesn't flow with the flow. It's imaginary lines that we just draw at a fixed location. And the fluid can pass in and out of this box by flowing through the edges. So on the left-hand side, if you imagine the flow is going in this direction, on the left-hand side of the box, mass can flow in. You're just bringing in material with the flow on the left-hand side. And on the right-hand side, a material can also pass out. And if the velocity is reversed, it can all be reversed. And we were thinking about a small box so that it has sides delta x, delta y, delta z. So there's a little volume, delta v equals the product of those three, delta x, delta y, delta z. And then the mass of that box would be equal to the density, basically evaluated at the center of the box, times that little volume. So our small box has little mass, rho delta v. And last time we started but didn't quite finish analyzing what's the relationship between these flows, the flow on the left-hand side coming in, bringing mass in, and the flow coming out the right-hand side bringing mass out, and the mass of the box. And what we found was that the rate of change of mass of this box was equal to this interesting, pretty simple expression, negative the little volume element times this thing here, which is the gradient operator dotted into the quantity rho u. And we mentioned this is called the divergence. So we're going to discuss this more today. But just in symbols, when we write this, gradient dotted into this quantity here, this is a vector, rho, the density times the velocity. How we interpret that is the gradient dotted into this is equal to the gradient vector, d by dx, d by dy, d by dz, dotted into rho u, rho v, rho w, which is that rho u vector. Which has three terms: the x derivative of the x component, y derivative of the y component, and z derivative of the z component of the plot. Okay, and so what we're going to do today is complete this derivation and derive what's called the mass continuity equation, which is the equation that's the analog of the Euler momentum equation, but it allows us to predict the density in the future rather than predicting the velocity field. And then we'll be basically one step closer to having a closed set of equations that we can actually solve to predict the full fluid flow. We sort of had five unknowns, three equations before, and this is going to be one other major equation that's going to bring us closer to having the equal numbers of variables in the nodes. Okay. Okay. So this is our so continuing on. So from here we had the rate of change of mass equals this expression here. So rate of change of mass, we can also write that as it's the change in the mass divided by the change in time. And our mass, we can recall, is the density times our little volume. And the key idea here in this particular setup is that the box is stationary. So the walls of the box aren't moving in any way. So delta x, delta y, and delta z are constant. So that means that the volume of this imaginary box is constant. So if we want to ask what's the change in mass as the mass is flowing in and flowing out, the change in mass just has to be related to any changes that are happening in the density. So our change in mass has to be related to change in density because our box is fixed. And so basically the idea is if more mass is coming in on the left-hand side than is leaving on the right-hand side, then the only way to account for that is that the density inside the box has to go up. So our density here is not constant. So we have here delta m over delta t equals delta rho, delta v, divided by delta t, and that equals our expression, negative delta v times the gradient dotted into rho u. What we see is we found something very similar when we were working on the Euler equation, that this little tiny volume of our box appears on both sides of the equation. And so we can cancel that out. So we can cancel out our volumes here. And then as delta t becomes small, this change in density divided by change in time, that goes to the partial derivative, partial rho, partial t. So so this is our normal little idea of our like sort of Leibniz style derivative. And the key thing is that the partial derivative is the appropriate derivative here because we're looking at a fixed point. The box is stationary, so we're just looking at this particular point in space, is the density increasing or decreasing? And so that's the partial. So we get here, the partial derivative of density with respect to time is equal to minus this thing here, which again, we're going to come back to this called the divergence. We're going to, I'm just going to keep talking sort of about how it connects to the physical derivation first, and then just in a few minutes we'll go back and talk about the divergence a little bit as sort of a mathematical point of view. Okay, so this equation here is now a complete equation. This is a regular PDE, and this is called the mass continuity equation. And you can stop here. So this is one way in which the mass continuity equation is written. You'll find it in textbooks written in this way. But I like to write it in an alternate form that is equivalent because it connects more nicely with the Euler equation. And so I just want to say here, this is a standard form. But we can also rewrite the equation using the material derivative. And so how we do that is by expanding out this thing that we have on the right-hand side, this divergence of the mass transfer. So we can expand. The divergence of rho u, as we wrote before, is d by dx of rho u plus d by dy of rho v plus d by dz of rho w. And now these are just ordinary partial derivatives, so we can use the product rule. So I'm going to break apart each of these three terms using the product rule. So we get here rho times d du dx plus u d rho dx plus rho dv dy plus v d rho dy plus rho dw dz plus w d rho dz. It's 6 terms from our original 3. And these terms come in two types. So in one set of terms, the rho is not differentiated and the velocity components are differentiated. So that says this term, and that term are all kind of similar. And in the other kind of term, the velocity is not differentiated, but density is differentiated. So we have these terms are of a second type. And in the terms with rho, we have a constant factor of rho outside all three, so we can factor. So factoring. We get rho outside of partial u, partial x, plus partial v, partial y, plus partial w, partial z. So that's these three terms combined that I just underlined once. And then the double underlined terms, we can note that this is u times the x derivative of rho, so it's the x component times the x derivative, this is v times d by dy, so the y component of the flow times the y derivative, plus the z component of the flow times the z derivative. And so that actually, you can notice, is actually the same thing as u dot grad of rho. We can also notice that this quantity here is equal to d by dx, d by dy, d by dz, dotted into uvw, which is equal to the gradient vector dot u. And so this divergence is showing up again. So we started off having a divergence, which again, we'll come back to that, the divergence of this density times velocity, and we end up now with two terms. One term which looks like our u dot grad, this is a very similar term to what shows up in the material derivative. In fact, it's the same term. And this other term is the densities outside multiplied by this divergence. So we get here rho times the divergence of u plus u dot grad rho. So all we've done here is we've just taken what we worked out when we were analyzing this box, and we've just used the product rule and some factoring to write it in a different form. And now that allows us to write our mass continuity equation in a form that, in my opinion, is a bit more natural with the language of fluid dynamics, which is, so using this, we can rewrite the continuity equation as, so we started off with partial rho partial t equals minus the divergence of rho u, and now we're saying that's equal to minus this expression we just wrote down, rho times the divergence of u plus u dot grad rho. And now, if we will just take this term here, which is the negative of u dot grad u, or u dot grad rho, and bring it over to this side, we get d rho dt plus u dot grad rho equals minus rho times the divergence of u. And this thing here, this is the material derivative, d rho dt. So in the end, we get our equation in the final form I'm going to use, d rho dt, the material derivative of the density is equal to minus the density itself times the divergence of the velocity field. And so this is the material derivative form of the continuity equation. Okay, so the two boxed equations are the same equation. They're exactly the same math, but just written in different ways. Just the derivatives are combined in different combinations, but it's the same. And I prefer this version because when we're talking about fluids, we often want to think about the fluid in terms of parcels moving around. And so that means we want to involve the material derivative. And so in this case, what this is saying is that as you have some parcel moving, as this parcel moves, its density is going to change according to whatever the local value of this right-hand side is. Okay. So we're going to return to the interpretation of this equation. But I just want to take a minute now to just talk about what is this divergence. We have the gradient dotted into a vector field, in this case the velocity. How do we interpret that? What does it mean, and how do we calculate it? So this section is called the divergence operator. Recall for any function f of x gradient f is a vector field called the gradient. We can also apply the gradient operator. And when we say a function, we mean a scalar function. So just a function of space, so a single number assigned to every location. But we can also apply the gradient operator to vector fields. F vector of x using the dot product. And so we write here the gradient dotted in to f is equal to d by dx, d by dy, d by dz, dotted into the three vector components, so fx, fy, fz, and that would give dfx dx plus dfy dy plus dfz dz. And so it's important to make sure, as always in fluid mechanics, that we understand the vector structure of this. So when you take a gradient, you start off with a scalar function, just a number as a function of space. And when you take the gradient, you get a vector. So as we've taken this gradient operator, which has a vector symbol, use it on f, and so we get a vector field out of it called the gradient. When you take a divergence, it's kind of the opposite. You start with a vector field, f of x, and then you take a dot product. And a dot product converts two vector things into a scalar thing. And so when you take the divergence of f, you get the sum of these three terms, but this is no longer a vector. It's not a vector. It is a scalar. Okay. So what does this mean? So let's do some examples. So just as an example, let's suppose f of x is just equal to the position vector x, which has components x, y, z. So just as a simple, probably the simplest function we can write down is just the linear function. So it's like f of x equals x, but we're in 3 dimensions, so it's the position vector. So what this function looks like, or what this vector field looks like, is actually let's just do it in 2 dimensions, x and y. So that's easier to draw. So we have x and y. So what this vector field looks like is it's the radially outward pointing vector. So our vector field looks like this. So this is what our vector field looks like. And now we can calculate the divergence. And we'll say, so the divergence of f is equal to dfx dx plus dfy dy, which is equal to d by dx just of x plus d by dy of just y, which is equal to 1 plus 1, which is equal to 2. So it turns out when we take this particular function, just the position vector, and we take the divergence of that, we get a constant number. So it ends up being it's not actually a function of x, it's just a constant. But we can see that it's a scalar, so it's a single number, it doesn't have any direction or anything like that. And the key observation is that this thing is positive. So it turns out to be a positive number. And then that helps our interpretation, because we call this thing the divergence. And so it sounds like what if it's like divergence, like when something's diverging means it's kind of spreading apart, or things are getting further away from one another. And so a positive divergence, it corresponds to a vector field that kind of looks like this, where if you imagine these vectors as velocities, it means that all these particles are all sort of spreading out from one another. So, so positive divergence corresponds to, you can think of it as spreading out or expanding. And I'll just also mention, actually, as a bit of notation here, I'm not going to use this much in this course, but you may see the divergence of a vector field F is sometimes written as div of F. We don't use that, but in vector calculus you might see that. You might see that notation. Okay. So that's a positive divergence. So how about a negative divergence? Well, probably a negative divergence would be something contracting. A positive divergence is expansion. The negative divergence is probably contraction. That's true. So let's do another example. Next, take f equals negative x. So it's the function negative x, negative y, which basically means, i.e., flip all the vectors. So if we just take, so we're taking now f is negative x, that's just simply the negative of our previous example. So what that means is that all of the vectors, if you just take the negative of the field, all of the vectors just reverse their direction. So now we have something that looks like this. So now we can calculate this. The divergence of f equals div f equals d by dx of negative x plus d by dy negative y equals negative 1 plus negative 1 equals negative 2, which of course is less than 0. And so when you have a negative divergence, that corresponds to contracting or collapsing or concentrating. And when I'm writing these words, contracting, collapsing, concentrating, these aren't like rigorous mathematical terms. These are just ways to think about what it means. When you have a vector field that has a negative divergence, that means it's kind of cramming everything together into a smaller space, and things are going to tend to contract and become more concentrated. And it's clear from a vector field like this, all the arrows are pointing towards the center. So if this is a flow, whatever material is just going to become increasingly concentrated at the center. And now to have a positive, and the key idea here is that if you have a more complicated flow field that's not just like radial or something, it maybe has some curvature to it or has some loops in it or something like that, the divergence still measures whether things are spreading apart or whether they're contracting. So even if you have a vector field or a velocity field that doesn't look exactly like this, if it has a positive divergence, that means things are spreading apart, and if it has a negative divergence, that means that they're coming together. And also negative divergence is also called convergence. So a velocity field or a vector field is said to be converging if it has a negative divergence. And so anyone who's taking the vector calculus course, you'll certainly see this later on in your course. But it's really easy. It's actually, in a way, the divergence is easier than the gradient because it's not a vector. There's not different components. You just sum up the derivatives and then you get a number, and that's what it is. So now let's use this idea about the divergence to now interpret our results for the mass continuity equation. So we can now interpret the mass continuity equation. So our equation was d rho dt, material derivative of density, equals minus the density itself multiplied by the divergence of u. And so let's imagine we have two cases. So case one, the divergence is positive. So when the divergence is positive, that means our flow is spreading out like this. So we imagine we have a parcel of fluid, maybe water, maybe gas of some kind. And if we look locally, so at the position of a particle, or sorry, a fluid parcel, that parcel has a velocity, but you can also ask what are the derivatives of velocity at that point. So the parcel is kind of moving through the derivatives of velocity. And so you could have this parcel where, for example, the velocity field local to the parcel kind of looks like this, and it's expanding. So this would be a divergent flow. So in this case, what would happen to a parcel? If you have a parcel and the velocities inside that parcel are kind of all going outward, what's going to happen to the shape of that parcel? Does anybody have any suggestion? Is it going to change, stay the same, get distorted somehow?
Does it deform?
Sorry?
Does it deform?
It does deform, yeah. And so in what kind of way would you say? If all the velocities are kind of, like imagine you have it's easier to think of it as a spherical particle, and then they're all going outwards. What would happen?
Would it grow?
It's growing, yeah. It's gonna like expand, kind of like if you like blow air into a balloon, right? That's exactly what happens. The air in the balloon is spreading out, and so the balloon just gets bigger. Now, the difference with the balloon is you're actually putting more air into the balloon that's making it get bigger. But in this case, it's just the walls are moving. There's no more mass being ejected to the center, just the walls are moving out because of the nature of the flow. And so what's going to happen here is the parcel is going to get larger. So the parcel expands. But when we have a parcel of fluid, we always make the assumption that how we define a parcel of fluid is we define a parcel as having the same molecules inside it. So you imagine you should have some fluid flow, there's like molecules everywhere, you just dye a cube of them, like color them red. And like those molecules now always constitute this particular parcel. So now when that parcel expands, the area, the volume that that red color occupies gets bigger, but there aren't actually more molecules in it. So what that means is the density is going to have to go down because those molecules get further away from each other. The volume increases, but the mass stays the same. The number of molecules stays the same. So we have volume increases, mass stays the same, and this is the definition of a parcel. So the density must decrease. And then sure enough, from our continuity equation, we have d rho dt equals minus rho times del dot u. The density is always positive. We've assumed that our divergence is positive. And so that means that our right-hand side of our equation, we have a negative times two positives, so that means it's a negative value. So as our parcel is moving, we're tracking its density. It's the material derivative of density. As the parcel moves, how does its density change? And the value is less than 0. So this means that as the parcel moves, its density decreases due to the expansion. So you can kind of think about it, like if you think about the balloon example, think about taking a balloon, but rather than blowing more air into it, just putting tape on your fingers and pulling the balloon out, right? So if there's the same amount of air in that balloon to begin with, as we pull the edges of the balloon out with the tape, the density of the air inside has to go down because it expands to fill the space, the density is going down. And the other case, of course, is when the divergence is less than 0. So case 2 is that divergence is less than 0. And that's like an example where we have our parcel, and now the velocities of the walls are now contracting in towards the center. And of course, that's going to squeeze the parcel down and make it smaller. So now in this case, this is convergent flow. So our parcel contracts. And so we have volume decreases, mass is constant, so density increases. And then again from our equation, we have d rho dt equals minus rho times the divergence. Rho itself is always positive, can't have negative density. We're assuming that in this case, the divergence is negative. So this is negative. So we have a negative out front times the density, which is positive, a negative times a positive times a negative. So we have a positive sign. So as the parcel moves, density increases due to contraction. Okay. So last time we did an example. I didn't actually talk about this in the review, but we did an example where we said, what if we just were given the density and the pressure? We said we had this linear pressure field and we had flow in a pipe. But what we did was we used the Euler equation, which was the du dt equation, to solve for the velocity field. And the key point is, whenever you have an equation like this, that is a time derivative of the density, this is now a partial differential equation that, if we actually know the velocity field, we can predict the density. And I actually meant to mention this at the beginning of class. The third assignment has already been posted, so I posted that over the break. But now I think you have the full, and it's due on Monday. And so now you have everything that you need to do the assignment. There's two questions. But one of the questions is to use this mass continuity equation to actually predict what the density will be if we know both the density at initial time and we know the velocity field. So the continuity equation and sometimes people say mass continuity equation, sometimes people just say continuity equation. Those are interchangeable. So the continuity equation is a partial differential equation, PDE, that can predict the density rho of x, y, z, and t. And so we're just going to do an example of how we solve this. And it'll be very similar to an example we previously did for the advection equation. So example. Solve the continuity equation to determine the density field in the presence of the velocity field of the flow u of x equals lambda x. And so this is what we call the straining flow before. We talked about this example before when we were talking about the kinematic equations. And so this flow, basically, if this is 0, here's x, the flow kind of looks like this. It's a flow that gets faster and faster as you go down as you go out to x equals infinity. Let's say assume the initial conditions. We also need the initial conditions, and the initial conditions are that rho of x and t equals 0 just equals rho naught equals a constant. So that's a uniform density. Okay. So we have this flow that we talked about before, and what we found the last time we analyzed this flow was back when we were talking about the kinetic equation. And we said if you put a cork in that flow, it's going to flow downstream, and as it flows downstream, it gets into areas of the flow that get faster and faster. And so as it moves, it starts moving faster and faster, and it ends up moving exponentially towards positive x. And so now we're asking not about how individual parcels move, but how the density field changes. And so I'll just ask. So if we have a parcel, and we put that parcel in this flow, the parcel is going to move downstream. And can anyone guess what's going to happen to this parcel? Is it going to stay the same shape? Is it going to change shape? It's going to move to the right, but it also is it going to become distorted, and in what way? Does anyone have any idea? This is a little bit subtle.
I mean, it would start elongating, no?
Elongating, that's right. So why is it going to elongate? What's the specific reason?
Well, because if this parcel has
finite extent, it has a small but finite volume.
Finite volume, then some part of it's going to be in at a part in the velocity field that has greater velocity than part previous to it. So it'll just start growing.
That's exactly right. So what Ben's saying here is that if this parcel has any thickness to it at all, so it's not a point, it's small, but it's an extended object, that means that the right-hand side of the parcel, the velocity gets faster and faster as you move to the right. So the right-hand side of the parcel is moving kind of a little bit faster, and the left-hand side is moving a little bit slower. So it means that as the parcel moves downstream, it's actually going to get elongated, and that's why we call this the straining flow. In general, in physics or in fluid mechanics or solid mechanics, we call this a straining effect. You take something and you stretch it out into a wire-like shape. And so if this is happening, what's going to happen to the density of those parcels? It's either going to stay the same, get bigger, or get smaller. Get larger or get smaller.
Decrease.
Sorry?
Would it decrease?
Decrease. And why is that?
Because there's a larger volume.
Yeah, and the mass stays the same, so you're stretching it out, the same amount of molecules are inside, so the density has to decrease. So this is another one of those cases where I always like, before I do any kind of physical calculation, to try to think about what's the answer likely to be, or what are the general properties of the answer before you do the calculation. And so in this case, we expect, just based on really simple physical reasoning. We expect that the density is going to decrease. So because parcels have finite extent, the right-hand side, RHS, right-hand side, moves faster than the left-hand side. So parcels become stretched or elongated. And so we expect density to decrease. Okay, so now we want to show that the continuity equation that we wrote down, this PDE that can actually predict the density field concretely, that actually agrees with our intuition, because this argument suggests that because of this straining effect and this stretching out of the parcels, that the density is going to drop, but we don't yet have a formula for like exactly how rapidly, like exactly in what way is it going to decrease. So let's do this let's now do the calculation. So we can calculate. So our equation is d rho dt equals minus rho times the divergence of u. And so we can just calculate now the divergence of u is equal to, in this case, in one dimension, we just have here d by dx, d by dy is basically 0 of lambda x. We have no flow. So here we have, so this is just d by dx of lambda x, which is just equal to lambda, which is a constant. So this is interesting. So the divergence of this particular straining flow is actually just the constant lambda. So that gives us actually an interpretation. When we write down the straining flow, what is this lambda? Well, it's equal to the divergence of the flow. This is a particular special flow where the divergence is a constant everywhere. So it's diverging everywhere all the time. So everything is always spreading out no matter where you look, and it's all spreading out at the same rate. The divergence is constant. So we have here in 1D, d rho dt equals partial rho, partial time, plus u d rho dx equals minus rho times lambda. And so we get here partial rho, partial t, plus lambda x d rho dx equals minus rho lambda. So this is our expanded form, our explicit form of the continuity equation. So in general, solving equations like this, it's a partial differential equation. In general, solving equations like this is a little bit tricky, and on the third assignment, I sort of walk you through an example where you can actually solve it exactly, even though it's a little bit more complicated. But the example we're going to do here is the sort of simplest case. So I'm going to say here, note, initially, at time equals 0, we have rho equals rho naught equals constant. So at least at time equals 0, the right-hand side of this equation does not depend on x in any way. We just have a constant value of our density multiplied by our constant divergence, lambda. So the right-hand side, so at t equals 0, the right-hand side does not depend on x. So what I'm going to do is look for solutions. I'm just going to kind of try to take the easy way out, and let's just look for solutions where it continues to be true that the density is uniform for all time. So this is really just kind of a guess, but we can, it's motivated by the fact that at least initially, the right-hand side doesn't depend on x, so maybe that stays true for all time. But the beauty of differential equations is that if we find a solution, it's very generally true, it's very often true, that if we find a solution, that solution is unique. So if we can guess the solution somehow, then we know that's the correct solution. So, so motivated by this, let's look for solutions. In which rho does not depend on x. So that means rho of x and t is really just rho of t, just only a function of time. And on the third assignment, you will loosen that restriction and do an example where it depends on both space and time. So in that case, so then we had here partial rho, partial t, plus lambda x, partial rho, partial x, equals minus lambda rho. And then because we're assuming that rho doesn't depend on x, that means that this term is 0, because it has no x derivative. And then this one here just becomes the ordinary derivative, d rho dt. So what we get here is just the ordinary derivative, d rho dt, equals minus lambda rho. And then this is the classic equation we've seen. You had an equation similar to this on, I think, some earlier assignments. It's even kind of similar to the one on the midterm, not exactly though. So we can solve this. d rho over rho equals minus lambda dt. Integrate from rho naught to rho of t. Integrate from t equals 0 to t. So we get log of rho of t over rho naught equals minus lambda t, which tells us that rho of t is equal to rho naught e to the minus lambda t. So density is exponentially decreasing. Like e to the negative lambda t. So now we've gone, just as we argued before, because these parcels are being stretched out as they go downstream in this straining flow, their densities are decreasing. And what we find from the concrete analysis in terms of using the continuity equation is that it's not just decreasing in some random way, it's decreasing exponentially at this very precise rate. And the rate of the exponential decrease corresponds to the strain rate or the divergence of the flow. So the sort of general conclusion here is that when you have a diverging flow, because remember lambda here was the divergence of our flow, and it was a positive divergence, so the flow is like spreading out everywhere. So when you have a positive divergence, locally that causes the density to kind of decrease exponentially. You're inflating the parcels because you're pulling apart the walls and spreading them out, and so the density is dropping exponentially as you do that. And so on the third assignment, you're going to do an example which is significantly more complicated than this, but it's broken down into several steps that guides you through the calculation. Okay. Okay. So what we've done so far this class is that we derived the continuity equation, mass continuity, and then we interpreted it in terms of the meaning of the divergence, where positive divergence is inflation, expansion, density drops. Negative divergence is contraction, density increases. But the whole goal, what we're trying to do, is we're trying to get a fully consistent closed set of equations to predict the whole flow. And we started with the Euler equation. We said we only have 3 equations for 5 unknowns, and now we have 1 more equation. So let's go back to counting equations. So let's return to counting equations. So now that we've added the continuity equation, we have du dt equals minus 1 over rho grad p. That's the Euler momentum equation from momentum conservation. Or F equals ma. And this gave us 3 equations. And we just added d rho dt equals minus rho del dot u. This is the continuity equation. Which comes from conservation of mass. And that gives us 1 more equation. And so 3 plus 1 was 4. So we're in a better spot than we were before. But we still have 5 unknowns. So we still need 1 more equation. So if we had 1 more, then we would be okay. We would have a closed set, and we could start calculating stuff, predicting the weather, predicting the ocean, whatever we want to do. So it turns out that these equations, the Euler, the momentum equation and the continuity equation, those are very general. So for any kind of fluid that you study, whether it's seawater or whether it's an ideal gas, whether it's something in stars, these equations will very generally be true. There might be a few extra things on the right-hand side. In the Euler equation, we've only incorporated the pressure force, but you can also incorporate things like gravity, rotational forces, maybe electrical forces. And so you can get more complicated forces on the right-hand side, but it'll still be called the momentum equation, some version of it. So you'll always have the momentum equation from conservation of momentum, and you'll always have the continuity equation. But where the last equation comes from depends a little bit more on the particular fluid that you're analyzing. And does anyone have a suggestion as to what kind of physical principle, or what we might use, what kind of idea, to get the last equation or the last pieces of information that will allow us to close this system? Anyone have a suggestion? We use conservation of mass. We use conservation of momentum so far.
Conservation of energy.
Energy, yeah. So something like conservation of energy, and as you know in physics, energy comes in different forms. We have potential energy, internal energy, kinetic energy, different things. So the nature of the energy conservation equation can really differ depending on what specific system you're looking at. But in general, something about energy is very likely to come. But to sort of illustrate that and to make it concrete, it really helps to focus on a specific system. So what we're going to do now for the next little while, at the end of this class, and then also probably for the next few classes, is we're going to discuss the specific phenomena of sound waves. And we're going to start by looking at sound waves in an ideal gas. And then the context of sound waves allows us to write down an energy equation that is going to close our system, and that will also let us predict all sorts of stuff about sound from first physical principles, from these kinds of ideas: momentum, mass, simple ideas like that, pressure, and we'll get sort of a full picture of how sound waves work as sort of an example of how we close fluid mechanics and how we get a consistent closed system. So, okay. So closing Euler plus continuity for sound waves in an ideal gas. So, as I said, so the momentum and continuity equations are very general and apply to basically any fluid situation. Often, our last equation comes from energy. The energy equation can take different forms depending on the situation. We will demonstrate this by studying the phenomenon of sound waves in an ideal gas. And then because this is an oceanography course, we're also going to do sound waves in water. We're going to start with an ideal gas because the physics of that is actually physics you all know already. So the equations that we're actually now going to use to close the Euler plus the continuity equation are all equations that you've actually seen already in courses in fluids or courses in thermodynamics. We're going to use the first law of thermodynamics, and we're going to use the concept of adiabatic motion, or adiabatic processes. The wind is howling. Okay. Okay. So, for an ideal gas, we immediately have one more equation, the ideal gas law, which is sometimes called IGL, for gas law. And so that is the equation. The pressure is equal to the density times the gas constant times the temperature. Okay, so we had 4 equations, we had 5 unknowns, and now this is another equation. So has this solved our problem or not? Can we just stop here, or do we need to do more stuff? What do people think? It's an extra equation. That sounds good. We're actually not done. Can anyone tell me why that is?
Because it doesn't depend on the position, maybe?
That's true. It doesn't. So it's kind of a local property, right? And it's kind of blending together all the local properties. So it doesn't. So it's true. It doesn't have like any time derivatives in it, things like that. But it's still actually an extra equation. So that's true, but that's not actually the reason. Any other thoughts? Is there any new variable in this equation that we haven't been talking about up till now?
Temperature.
Temperature, yeah. So we thought we were smart, right? We wrote down the ideal gas law. That's great. That's a new equation. But when we did it, we accidentally introduced a new variable, the temperature. So we gave ourselves an extra equation, but we also gave ourselves an extra variable at the same time. So we're actually kind of back where we started. This is useful, but it doesn't actually solve our problem. So although this is an extra equation, it also introduces a new unknown, the temperature. So we still need one more equation. And as was suggested, that equation is going to come from ideas of energy. So energy conservation and in thermodynamics, you probably would have seen this called the first law of thermodynamics. And you may have seen the formula du equals dw plus dq. Does this formula look familiar to people? You've seen it in some context before? No? Okay. Okay. So in this formula, so U is the internal energy of the gas. And this is really the change, because the little d means this is the differential change. We imagine the system has changed in some small way, the internal energy is going to adjust a little bit, and then W here is the work done, and Q is the heating. And so this equation really expresses the sort of flow of energy, that energy can't be created or destroyed. It can only be transformed and passed from one object to another and transformed into different kinds of energy. And so what this is saying is that the internal energy of the gas changes by 2 mechanisms. One, you can do work on the gas. So just like when we do first year mechanics, if you push an object, you do work on it, and that speeds the object up. It adds kinetic energy. So when you exert forces and you do work on an object, you can give it energy. And the other way is you can heat it up. So you can just transfer heat, that molecular thermal energy, into an object. In this case, maybe it's a parcel of air. And that's another way you can increase the internal energy. So the internal energy is modified by 2 processes, work and heating. And this is essentially the statement of conservation of energy. Okay. So for an ideal gas, the work done on the gas is equal to minus the pressure times the change in volume. This is probably also a formula that you would have seen in some kind of thermodynamics course. And we're not actually going to do a lot of thermodynamics here. We're just going to kind of get to a formula that's going to close our system, and then we're going to just be good and go on with our fluid mechanics. But I'm showing this because it illustrates how fundamentally conservation of energy is the final ingredient that comes in and closes the system. And it fundamentally comes down to the first law of thermodynamics. But obviously, if we're going to use this equation, we have to somehow relate energy, work, and heating to stuff we're already using, like density, pressure, velocity, stuff like that. Because otherwise, if we introduce more variables, we're going to be back in the same situation with too many variables and not enough equations. So for an ideal gas, the change in work, so the work that's done is minus the pressure times dV. And the way we can think about this is if dV is positive, that means our gas expands and does work on the environment. So dW is less than 0. So basically, you have a little parcel of gas. If it expands, if its change in volume is positive, that means it has to push away the other air that's surrounding it. So it's doing work on that air. So when something does work, it loses energy. Whereas if dV is negative, that means gas is compressed. Work is done on it. So work is done to squeeze the gas in, and when you push and squeeze something in, it raises the energy. And that's why generally, you've probably had this, but maybe, I don't know, if you pump up bicycle tires, if you do that, when you pump a lot of air into something, you compress it, it gets hot. And that's the reason is because you're doing a whole bunch of work compressing this air, and that heats it up, it raises the temperature. Actually, it doesn't heat it up, it raises the temperature, because it's work, not heat. Okay. So if the change in volume is negative, the gas gets compressed, work is done on it, and dW is greater than 0. So this work term can either add to the internal energy, or it can reduce it, depending on whether the gas is expanding, doing work on the environment, or if it's getting squished and work is being done on it. This looks pretty good because we want to relate dW. We want to relate everything in this equation to things we already have. Pressure we already have, and volume is kind of like density. Volume is sort of like 1 over density. So that's a start. And I'll just write down the last sentence here. So what about dQ? So this is heating, heat transfer due to processes like thermal conduction or diffusion of heat. So the idea here is, let's say we have two parcels that are next to each other, and this one is warm and this one is cool. Then there will be just due to random motions, there'll be a flux of heat from the hot one to the cold one, Q. And that's just due to you put two objects together, a hot and a cold object, and heat is going to flow from the hot one to the cold one. But it turns out this process is quite slow. So we will be more concrete later. But this heat process, this heat transfer is slow. So we're going to come back to what we mean by slow. We'll do an explicit calculation. But for now, just think about it as sound waves oscillate hundreds of times per second. We often measure them in hertz. So hertz is kind of like per second. So a middle C, for example, is 512 hertz. Wait, was it 256? Either 256 or 512. Right? And so you get hundreds of oscillations every second. So that's a very fast process. And this is very, very slow. So we can basically ignore the heat transfer if we're just thinking about waves. So sound waves oscillate hundreds of times per second. Which I'm going to say is fast. So for sound waves, we can ignore dq and say dq is basically equal to 0. And you probably have seen this before. When the heating is 0, we call that adiabatic. Adiabatic motion just refers to motion where it's happening so quickly that there's no time for heat to be transferred by these random molecular motions. The like bumping up of molecules against each other transfers heat very slowly. And so if you're thinking about something that oscillates very quickly like a sound wave, you can basically ignore any kind of slow heating due to slow molecular thermal type of dynamics. Okay, so we'll stop there. And next time we'll come back and we'll finish off the first law of thermodynamics. And we'll actually use this adiabatic idea to get one more equation that will close our system and allow us to study sound waves and predict all sorts of interesting physical properties of those waves. Okay, great. So please take a look at the assignment that's been posted. If you have any questions, just let me know. If you haven't picked up your midterm, it's right here at the front. And I will see you all on Thursday.